May 25th, 1998. Astronomers and technicians from ESO, the European Astronomy Organization, are preparing for the night's observation at the Paranal Observatory. They are experienced professionals, and to the uninitiated, it may seem like a routine operation. But this night is a very special one. It is the night of First Light with a new giant telescope. First Light is the equivalent of a maiden flight of a new type of aircraft. The telescope that will open its eye on the sky for the first time is one of the largest and most advanced optical instruments in the world. It is part of an extremely ambitious science project that marks the entry into a new era for astronomical research. Will it live up to the great expectations of all the astronomers, engineers, opticians, detector specialists, and many other people who have worked on this project for so long?
Yes. So it works.
Over 5,000 people have been involved since the first idea about this super instrument was born more than 20 years ago. This is the moment they have waited for.
Many times. It works.
That's the one, huh?
Oh my God. Watch out.
The ESO Very Large Telescope, or for short, the VLT, is the prime representative of a new generation of extraordinarily powerful telescopes based on novel technological concepts and new materials. The VLT will be the world's largest and best optical telescope at the beginning of the 21st century. The VLT is not a single instrument, but an array of telescopes, which can either work together with the light-collecting power of a 16-meter telescope or independently. Each of the giant mirrors is only 18 centimeters thick. They are flexible and thus require a computer-controlled support system. The core of the VLT consists of four 8.2-meter so-called unit telescopes. Each of them has several foci, where the faint light from celestial objects will be captured by different auxiliary instruments. However, the most powerful mode of operation is when the light from all of the telescopes is combined coherently. When they work together in this way, the telescopes form a giant interferometer that allows astronomers to study celestial objects in unprecedented detail. With the addition of movable 1.8-meter telescopes mounted on tracks, the performance of the entire array will be even further improved, as the baseline, meaning the distance between the individual elements, can be increased to as much as 200 meters. This configuration, known as the VLT interferometer, will produce images of unprecedented sharpness. It will, in principle, be possible to see astronauts on the surface of the Moon. Before this enormous potential can be fully exploited, a fundamental problem must be solved. As light from a star passes through the terrestrial atmosphere, it is influenced by turbulence, pockets of air moving quickly up or down. We can see this effect as the twinkling of the stars. In the telescope's focal plane, it produces an irregular motion of the stellar image, as seen in this computer animation. This severely degrades the sharpness of the recorded image of the star during long exposures. But the problem can be overcome. ESO and research centers in France have jointly developed a new device which is capable of real-time adjustment of the distorted light. The heart of the instrument is a small deformable mirror that is placed in the light path in front of the detector. By rapidly changing its shape, it is able to continuously refocus the light and thereby produce much sharper images. Thanks to this advanced optical technique, the telescope now performs nearly as well as if it were in space, above the disturbing atmosphere. The VLT is one of the most ambitious science machines that mankind has ever built. It embodies totally new concepts and ideas of design, manufacture, and operation. All through the project, ESO engineers used sophisticated computer simulations that allow them to predict the ultimate performance of the telescope. The VLT has been an enormous challenge to European industry, which has played a key role in the project. Novel manufacturing methods and new technologies had to be developed. In some cases, even completely new manufacturing plants were constructed. The VLT primary mirrors are monoliths, single pieces of glass. Until the VLT, no one had ever cast a mirror of this enormous size. For this, a new manufacturing technique was developed by the Schott Glassworks in Mainz, Germany. We are witnessing the casting of one of the giant mirrors. At 1400 degrees Celsius, 45 metric tons of molten glass are poured into the mold. By spinning the mold during the first cooling phase, the glass assumes a rough meniscus shape. During the following production phases, the glass is transformed into zero-dur, a glass ceramics material with a thermo-zero expansion coefficient, important for retaining the optical quality of the VLT. At every process stage, very detailed quality control is essential. Riosc, the French optical company, performs the polishing of the giant mirror blanks. State-of-the-art interferometers probe the accuracy of the mirror surfaces as the polishing proceeds. They are installed at the top level of a 30-meter high test tower. In 1995, after 2 years at Riosc, the time has come for the detailed acceptance tests of the first of the primary mirrors by ESO's engineers. Careful measurements show that the final optical surface is correct to within 500 thousandths of a millimeter. This corresponds to an accuracy of only 1 millimeter deviation over a surface with a diameter of 165 kilometers, as large as the entire area of Paris. All in all, the manufacturing sequence for one mirror has lasted nearly 4 years. This incredible performance must be matched by all other components. The mirror cell, with its unique combination of electromechanics, hydraulics, electronics, and telescope and instrumentation interfaces, as well as the main mechanical structure, weighing 430 tons. The structure floats on a very thin oil film. High-precision drives and motors move the telescope with pinpoint accuracy. To build a telescope like the VLT is an extreme challenge to the engineers. They must combine heavy and bulky structures with ultra-high precision. Specialist companies from all over Europe participate in this great venture. To verify the functionality and compliance with the demanding technical specifications, a complete test assembly of the first of the giant telescopes was carried out at Ansaldo in Milan. Every single piece must fit exactly as the structures are put together. This is followed by thorough testing by ESO specialists before the telescopes are shipped to their final destination, the VLT Observatory in Chile. Antofagasta, capital of the second region of Chile. The town proudly describes itself as the window on the sea and the gate to the desert. The port of Antofagasta serves the ships that bring in the heavy telescope structures. ESO has established its VLT office there. Behind this bustling town lies the vast expanse of the Atacama Desert, one of the most arid places on the surface of this planet. Here, nature has created a remarkable climate. Despite its inhospitable appearance, it is one of the sites best suited for an astronomical observatory. The cold Humboldt Ocean current running along the Pacific coastline of Chile and the impressive Andes Range to the east create protective barriers against clouds. The land in between is exceedingly dry and provides up to 350 cloudless nights a year. The view from an aircraft flying along the Pacific coast shows the dramatic change in climate between the humid coastline and the desert region. Specialists from ESO surveyed this area for a decade in order to locate the best possible site for the VLT. Their choice fell on a 2,664-meter-high mountain, 12 kilometers inland from the Pacific Ocean and some 130 kilometers south of Antofagasta, Cerro Paranal. To start with, 28 meters or 350,000 cubic meters of rock had to be removed from the mountaintop in order to create a sufficiently large platform for the VLT. For years, this has been a busy building site, the workplace for hundreds of construction workers and engineers. Specialists of many trades and professions had to work hard before the scientists could train their new super telescope on the sky for the first time. December 1997, MS Tarpon Santiago approaches the port of Antofagasta. In its hold, the first 8.2-meter mirror for the VLT. Slowly, it is lowered from the ship and placed on a special carriage. Now it must travel the long and dusty road through the desert to Cerro Paranal. The journey starts on the following morning. The convoy with the mirror moves no faster than 6 kilometers an hour. On the rough desert road, it slows down to a mere 3 kilometers an hour. It takes 3 days to reach the destination. Detailed measurements and careful visual inspection confirm that the precious but fragile piece has arrived in good shape. 4 months later, in April 1998, at the Mirror Maintenance Building, the mirror is mounted in its supporting structure. This mirror cell is itself a technological masterpiece. It contains the sophisticated system of computer-controlled active support elements for the mirror. Weighing only 10 tons, it holds the 22-ton primary mirror in the perfect position and also carries heavy auxiliary instrumentation. As the mirror, with its cell, is attached to the telescope, the time has come for the critical alignment of the entire optical system. The exciting moment of first light is approaching when the first astronomical objects will be observed with the VLT. The countdown has begun. But even the best telescope is useless without perfect instruments. National research institutes from all over Europe work with ESO to develop the first generation of advanced instruments for the VLT. Some of the best scientists and engineers of the continent do their utmost to ensure that the VLT will be equipped with cameras and spectrographs of outstanding performance. Such instruments are exceedingly complex, each containing over 20,000 individual parts. The VLT will have a large complement of instruments. The first of the 4 large telescopes will begin regular science operations with 2 instruments, FORS and ISIC. They will be the true workhorses of the VLT. They both contain complex cameras and spectrographs that will explore the near and distant universe at visible and infrared wavelengths far beyond current horizons. FORS is developed and built by a consortium of German research institutes. ISIC is built by ESO. Other consortia in ESO's member countries work on additional instruments that will be mounted at the many VLT foci. The VLT must undergo extensive testing. The telescope and all its intricate subsystems are fine-tuned to prepare it for regular science operations. But the astronomers cannot wait. They obtain many spectacular images with the new telescope already during the test phase. The observation with the FORS camera shows the spiral galaxy NGC 1232. With a diameter of 200,000 light-years, it is twice as big as our own galaxy, the Milky Way. Its distance is about 100 million light-years. Despite this enormous distance, the excellent optical quality of the VLT and FORS allows us to see an incredible wealth of details. Another photo shows a sky field in which a peculiar, quite remote cluster of galaxies is seen. It consists of a large number of faint and distant galaxies that have not yet been thoroughly investigated. The beautiful spiral galaxy NGC 1288 in the southern constellation Fornax. This galaxy is 300 million light-years away from us. This dramatic infrared picture, taken with the ISAC camera, shows two galaxies that are merging. The stars in them do not actually collide, but gravitational effects can set off strong bursts of star formation. This is exactly what happens here, especially in the blue complex below the center. Much closer to home, another FORS picture reveals fine details in the Dumbbell Nebula at a distance of around 1,200 light-years. The Dumbbell Nebula consists of very rarefied gas that has been ejected from the hot central star at its center, that is now in one of the last evolutionary stages. The gas atoms in the nebula are heated by the intense ultraviolet radiation from this star and shine in strong colors. This is an ISAC image of the star-forming area RCW38. At a distance of about 5,000 light-years, the stars which have recently formed in a cloud of gas and dust are still deeply embedded in this dusty cloud. The cloud is so dense that if it were in front of the Sun, it would hide the Sun completely from view. Not even the largest telescope on Earth would then be able to see our central star. But infrared radiation gets through, and ISAC can easily see the stars of RCW38. Further out in space, ISAC has observed some strange-looking arcs in the sky. They are caused by gravitational lensing, a kind of mirage that was predicted by Einstein. In reality, these arcs are the heavily distorted images of faraway galaxies, whose light has been bent by a massive object located between the galaxies and us. Heavy galaxies and clusters of galaxies cause this effect. Gravitational lenses amplify light. Acting like natural telescopes, they let us look into the most distant corners of the universe. From the farthest depths of space, the border of the observable universe, to the hidden birthplaces of stars and planets in our home galaxy, the VLT is now opening wonderful new perspectives for scientists. What will we see? Which surprises await the inquisitive eyes of the giant VLT? For centuries, mankind has wanted to know what was beyond the current horizon. The VLT is beginning to lift the curtain and let us glimpse into the unknown. We are on the verge of a new age of discoveries.